Hello friends, so today we are going to solve the question from heat and thermodynamics. From the year 2010 we are having 4 questions, 2011 2 questions, and from the year 1999 1 questions. So in total we are going to solve 7 questions. So first question, it was asked in the year 2010 and it states that a piece of ice, heat capacity 2100 and latent heat as 3.36 into 10 to the power 5 of mass m gram is at -5 degrees centigrade at atmospheric pressure. It is given 420 joule of heat so that ice starts melting. Finally, when the ice-water mixture is in equilibrium, it is found that 1 gram of ice has melted. Assuming there is no other heat exchange in the process, the value of m is. So we have to find out the mass of the ice, and in this case we have to remember that only 1 gram of ice has been melted. Okay, it means the heat was only sufficient to melt 1 gram of 1 gram of ice. Okay, and so in this case, first of all we have our initial state, and initial state is only having our ice. In this initial state we can say we are given as ice, and ice is having a mass of m gram and at a temperature of -5 degrees centigrade. -5 degree centigrade, and heat that is added here given is 420 joules. Heat input is our 420 joules, and final state it states that the ice and water mixture is in equilibrium. Okay. So we can see our final state. It states that ice water mixture is in equilibrium. Okay. And it is also given that 1 gram of ice melts, or we can say it becomes water at 0 degree centigrade. Okay. And also there is no heat loss. It means entire heat is only you can say used for the conversion of ice into water. So in this, let us try to understand what is the process involved. So first is our heating of ice from -5 to 0 degree centigrade, and okay, and secondly we are given that the initial mass of the ice is m and only 1 gram is melted. Okay. Therefore, we can say that the final mixture at 0 degree centigrade is going to have m minus 1 gram of ice and 1 gram of water. Final mixture is at 0 degree centigrade with m minus 1 ice and 1 gram of water, because only 1 gram of ice is melted. And first of all, now let us find out the heat required. And this heat required will be of our, you can say, two-step process. First will be the heating of ice from -5 degree centigrade to 0 degree centigrade, and then it will be melting of the ice at 0 degree centigrade. Okay, so it will be a two-step process. So for the first step is our heating of ice from -5 to 0 degree centigrade. And let us suppose that heat is given as Q1, which will be equal to mass m, our specific heat of ice, and we have our this delta T. And we can just substitute the value we get from here, that our Q1 mass is given as m itself, and it is not latent, but the heat capacity. C is our heat capacity, which is given as 2100 per kg. Okay, so we can easily convert into grams. So this will be coming as our 2 by 1, and change in temperature will be our 0 minus of -5, and this gives us 10.5 times m joules. Now we come to our second step. Second step will be melting of 1 gram of ice at 0 degree centigrade, and let us suppose that is given as Q2. So Q2 will be equal to mass which is melted multiplied by its latent heat of fusion. Okay. And mass melted is our 1 gram, so we get our Q2 is equal to 1, and we have this as our 336. Everything is in grams, so we just convert it into grams. So this is 336, which gives us 336 joules. Now the final temperature is 0 degree centigrade. Okay, so we have to keep in mind. Now we can easily apply the energy conservation. Heat supplied, which is our 420, will be equal to total heat consumed, that is Q1 plus Q2. And we simply substitute the values, we get this as 10.5 m plus 336 is equal to 420, and we get this as our 10.5 m is equal to 420 minus 3 36, that will be over 84, which gives us that the value of mass is equal to 8 grams. So the initial mass was of our 8 grams. Next question. It was also asked in the 2010, and it states that two spherical bodies, A radius 6 cm, B radius 18 cm, are at temperature T1 and T2 respectively. The maximum intensity in the emission spectrum of A is at 500 nanometer and in that of B is 1500 nanometer. Considering them to be black bodies, what will be the ratio of the rate of total energy radiated by A to that of B? So this is directly based on our Stefan-Boltzmann law. Okay. So we can write that our Stefan-Boltzmann law, and which gives us that our power radiated, that is P, is equal to our sigma, and we have this is area and temperature raised to power 4. So we have two bodies, so accordingly we can divide this formula into two parts. So we can say for body A, we can write this as P of A is equal to sigma, and area we can write because this is spherical, so we can write this as our 4 pi RA square and TA whole raised to power 4. And similarly we can write for body B will be equal to our PB is equal to sigma 4 pi RB square, and this we have TB whole raised to power 4. And okay, and we also need to find out, because temperature is not given to us, so let me first of all find out the ratio, then we can deal with the temperature part also. So we can say our PA upon PB will be equal to sigma 4 pi RA square upon TA4 sigma 4 pi RB square, and this we have TV reversed of 4. These two terms cancels out, and radius we know, radius is given as 6 as well as 18 centimeter. So this comes as our 6 upon 18 whole raised to power square, and this is our TA upon TB whole raised to power 4. Temperature is not given to us, but we are given the wavelengths. Okay, maximum intensity 500 nanometer as well as 1500 nanometer is given to us. So for this we are going to use Wien's displacement law. So you can say Wien's displacement law, which gives us that the maximum value of our wavelength multiplied by the temperature is equal to constant, which is represented as B. Sometimes it is also called as a Wien's constant, Wien's displacement constant. Therefore we can write that our lambda minimum for A, temperature for A will be equal to lambda minimum for B, and we have temperature of B. And from here we can find out the ratio TA upon TB will be equal to our, sorry, it's not lambda minimum but lambda maximum. And here also maximum. So this comes as lambda max, and this here divided by lambda max of B and lambda max of our A, and we substitute them. We get that our PA upon PB will be equal to 16 goes by our 3, so we can write this as our 1 upon 9 multiply by, and lambda max of B is our 1500 and lambda max of A is our 500, and both are nanometer. There is no need to convert because it is only ratio, this whole raised power 4, and this goes by 0 and 5 goes by 3, and let me write it here as 3 raised power 2. So we can write this as our 1 upon 3 raised power 2 multiply by 3 raised power 4, and this goes by 2. So this ratio will be equal to over 9. Next question. It states that it was also asked in the 2010, a diatomic ideal gas is compressed adiabatically to 1 upon 32 of its initial volume. If the initial temperature of the gas is T1 in Kelvin, find the final temperature, and the final temperature is A multiplied by Ti, sorry, it is Ti not T1, the value of A is. So basically it is adiabatic process, and the volume ratio is given to us, which is our 1 upon 32. So we can just use directly our formula for our adiabatic process. So you can say for adiabatically compressed process, let me write it adiabatic process. Adiabatic process, we can write that our temperature volume raised to power gamma minus 1 is equal to constant, and we know our gamma is our adiabatic ratio. Gamma is it is adiabatic ratio or adiabatic index. Adiabatic index, and which is nothing but our C of P upon C of V, and we already know their respective formula, that is our 7 upon 2 times R, and this comes as 5 upon 2 times R. Here this 2 R and R cancels out, so this ratio comes as our 7 upon 5. And we need to find out gamma minus 1, so we can just substitute it. We can write this as gamma minus 1 will be equal to this ratio, we can write this as 1.4. So 1.4 minus 1 is equal to 0.4, and this is adiabatic process, so we can just apply the condition: temperature initial, volume initial, gamma minus 1 will be equal to temperature final, volume final, and we have this as gamma minus 1. And we are given that the final temperature is A times our initial temperature, and we are also given that our final volume is equal to 1 upon 32 of our initial volume. Okay, so we simply replace them, and we can write this as our T initial, volume initial, and gamma minus 1 is our 0.4 is equal to Tf is our A times Ti, and this comes as 1 upon 32. We can write this as 0.4, and this is Vi 0.4. Here this Vi and Vi and Ti cancels out. Therefore, we can write from here that our A is equal to 32 raised to power 0.4, and we can write this as 2 raised to power 5 whole raised to power 0.4, and therefore we get that our A will be equal to 2, and this we can write 5 multiplied by 0.4, which comes as 2 raised to power 2, giving us value of A is equal to 4. Next question. It states that it was also asked in the 2010, 1 mole of ideal gas in initial state A undergoes a cyclic process ABCA as shown in the figure. Its pressure at A is P0. Choose the correct options from the following. So it is basically multi-correct, or it could be a single correct. We'll just find out. So basic figure is given to us. Start from A, go to B and back to C. Okay, A to B is our isothermal, and B to C is simple our line process, which we can just find out with the help of the equation of the line also. And C to A is our, basically we are having our volume is our constant. Okay. So first of all, let's write the states which are given to us. We are given that our A is having a pressure is given as P0 and volume is our V0, and our, let's write in the form of temperature. Temperature is, so we can write this as V0 T0, and B is having our 4 V0, temperature is T0, and our C is having a volume of our V0 and temperature, let us suppose, is our Tc. Okay. And obviously Tc is less than our T0, that from this particular point we call this as our Tc. And 1 mole is given to us, so we can use our ideal gas equation. Ideal gas equation, which gives us that a PV is equal to nRT, and so we can write that our, for 1 mole at point A, we can write this as P0 V0 is equal to R times T0, and this is specifically for our A. Let's check option number A, which states internal energy at A and B are same. We know that the internal energy is basically our temperature dependent, and process A to B is our isothermal, so therefore we can say that it is true. So we start with option A, and we can say that our internal energy suppose that is represented as U is directly proportional to temperature. Okay. And from the figure itself, temperature at A is equal to temperature at B is equal to T0. Therefore, we can say internal energy at A is equal to internal energy at B. So this option is correct. Part B, work done by the gas in the process AB is P naught V naught natural log of 4. So we have our option B, and option B is basically isothermal. Sorry, process AB is isothermal. So you can say our A to B is isothermal. Therefore, work done of process of AB will be integration initial volume V naught, final volume 4 times V naught is equal to, and this is equal to P dV, or we can say P naught dV. Okay. And this, from here we can find out of P naught. P naught will be equal to R T naught divided by V naught. So we can write that our work done WAB will be equal to our V naught 4 times V naught, and this comes as our R T naught upon V naught dV. And this we can just change into our dV naught because of the substitution. So this will be becoming a natural log of V naught. So this will be our R T naught natural log of V naught, and the limits goes from our V naught 4 times V naught. Therefore we get our WAB is our, and RT naught we can write P naught V naught. So this comes as P naught V naught, and substitute the limits natural log of 4 V naught minus natural log of V naught. Now this is quite simple calculation. V naught we can write this as our, in the ratio, natural log of 4 V naught divided by V naught. V naught and V naught cancels out. So we get our work done AB will be equal to P naught V naught natural log of 4. So therefore option B is also correct. Now we come to the option C. Option C states that pressure at C is P naught by 4. Okay. And we can just use our ideal gas equation because the volume is our V naught. So we can write our pressure at C will be equal to R Tc upon V naught. Okay. And in terms of temperature, we can write this as P naught Tc by T naught. Okay. And we already know that our Tc is less than our T naught. Okay. And therefore we can be very sure of that our Pc will be less than P naught. Okay, this is true for it. Okay. But in this particular case, we are not given any value of P naught, only we know that it's less than P naught. So this option is not true. Okay, or we can say we cannot conclude actually. Okay, it's difficult to find out unless and until we know what will be value of our this temperature relationship. Okay. So this we can say not correct. And we come to option D. And option D we are given that temperature at C is T naught by 4. Okay, once again same, because nothing is being mentioned, so we are not very sure what will be the temperature. So this, about this we are not very sure that it is correct or not. We will know that Tc is less than T0, but what is the actual value, we are not aware of that. Therefore we can say not correct. Okay. Next question. It was asked in the 2011, and it states that a steel wire of length L at 40 degrees centigrade is suspended from a ceiling. Then a mass m is hung from its free end. The wire is cooled down from 40 degrees centigrade to 30 degrees centigrade to regain its original length L. The coefficient of linear thermal expansion of the steel is 10 to the power minus 5 degree per degree centigrade. Young's modulus is 10 to the power 11, and radius of the wire is 1 millimeter. Assume length is very much larger than the diameter of the wire, then the value of m in kg is nearly. So this question we can just draw an approximate diagram in two parts. In the first part, we are having our wire and whose length is given as L. And in this condition, which we can call as initial condition, there is no mass attached to it. Okay. So let us call this as our initial condition. And in this initial condition, we are having that length is L, and temperature is 40 degrees centigrade. Okay. And then a mass is hung to it. So we are having that a mass is attached to its free end, and suppose this is the mass m which is attached to it, and its length is extended. Let us suppose its length becomes now L plus delta L. This is the total length. Okay. And then there is a third diagram or third figure we can draw when the temperature is decreased to 40 degrees centigrade and this length is returned back to our L. So we can just, but mass is still attached to it. Okay. So we have this mass m and length is once again our L, but in this case now the temperature is 40 degrees centigrade, sorry 30 degrees centigrade. Temperature is our 30 degrees centigrade. Okay. And let us call this as a final condition. And this is our intermediate. Condition. Okay. So obviously the main difference between, you can say, when the temperature is reduced from 40 degrees centigrade to this 30 degrees centigrade, there will be, you can say, thermal contraction in the wire. Okay. And by the change in temperature, that is delta T is 10 degree centigrade. So let us discuss this thermal contraction. And So we can say the change in temperature delta T will be equal to 40 minus 30, that will be 10 degree centigrade. So from here we can say that the change in length due to this thermal contraction, or we can call it thermal contraction for the time being, change in length due to thermal contraction. Let us say delta L will be equal to over L multiplied by alpha multiplied by delta T. And all these values are given to us, so we simply substitute it and find out our delta L. So we get this delta L will be equal to L 10 raised to power minus 5 multiplied by 10, which gives us 10 raised to power minus 4 times L. Okay. And we have to remember that this will be the extension, okay, or this is the amount by which the wire is shortened if no external force is applied. So we can say that this is the amount by which wire would shorten if no external force is applied. And now when mass m is hung, so in the downward direction we are going to have force that will be equal to over mg. So we can say that our initial stretching due to mass, or we can just write it stretching due to mass. Stretching due to mass, and we have to remember this stretching is still at our 40 degree centigrade. Okay. So we can say this will F is equal to over mg, and we can find out our area of cross section, and because we need to find out the stress, so we can say the stress is equal to our force oblique area, and force is our mg, and area will be over pi r square. So this covers our mg pi, and radius is given to us at 10 raised to power 1 millimeter. So this comes at 10 raised to power minus 3, or we can say 10 raised to power minus 6. And from here we can find out our, because we need to find out our delta L, which we are going to make a comparison. For that we are going to use our Young's modulus. So we know our Young's modulus, that is Y is equal to the stress oblique strain. This comes as a sigma oblique and strain is our change in length oblique original length, and this strain is because of the weight, so let us call this a delta L mechanical divided by L. And here we can write this as force oblique, or we can write our let me write this as our sigma. We can just later on change. Okay, from here we are going to find out this delta L mechanical, so we can write that change in length because of the mechanical force will be equal to our sigma times L divided by Y, and sigma is our mgl, and this comes as a pi 10 to the power minus 6, and Y is given to us at 10 to the power 11. So we get this as our mgl, and this we have a pi into 10 to the power 5. It means that at 40 degrees centigrade, at 40 degrees centigrade, the wire is stretched, wire stretches rather, wire stretches by delta L mechanical, which due to mass. Due to mass. Now it is given that at 30 degrees centigrade it returns back to its original length. Okay, so we can call that as a equilibrium at 30 degree centigrade. Equilibrium at 30 degree centigrade. Now in this case we have to remember that if there was no mass, then the length would be more shorter because of the thermal contraction. Okay, so we have to keep this in mind. So we can say that at equilibrium at 30 degree centigrade, or from here we are given that wire returns back to original length, that is our L. So we can say that without any mass, the natural length of the wire at 30 degree centigrade would be shorter due to thermal contraction. Due to thermal contraction. Therefore, we can write that our natural length at 30 degree centigrade natural length at 30 degree centigrade, let us call this as L natural at 30 degree centigrade, will be equal to original length minus our change in length because of the thermal. And so this is a change in length. Let me call this a thermal, and this is a thermal. So we substitute it, we get this is equal to over L minus 10 raised to power minus 4 times L, or we can say L 1 minus 10 raised to power minus 4. And now we can say the mass is attached. So we can say that our when mass is still attached, the wire is stretched to length L. Therefore, we can say the extension from natural length at 30 degrees centigrade, and we can write the equation that our delta L mechanical at 30 degrees centigrade will equal to L minus L natural at 30 degrees centigrade, and we get this is L minus L 1 minus 10 raised to power minus 4, and obviously this will be coming as 10 raised to power minus 4 times L. And this extension we know is called by the Young's modulus. Therefore, we can write that our delta L mechanical at 30 degrees centigrade will be equal to our mgl times area multiplied by y, and this comes as 10 raised to power minus 4 times L, and here this L and L cancels out. Therefore, we need to find out the mass. So we can say our mass M will be equal to 10 raised to power minus 4 times area Young's modulus divided by G. We substitute the values, and that is 10 raised to power minus 4 times our pi r square. I think area we found out also. Yeah, and this comes as our pi r square 10 raised to power minus 10 raised to power 5. So we get this as our pi 10 raised to power 5, and G is our suppose 9.8. This will be equal to over 10 pi divided by 9.8. So we get that our mass will be approximately equal to 3.20 kg. Okay, we can approximate it as 3 kg. So this problem was quite tricky to solve because it consists of multiple parts. multiple part means initially it was length L. When mass is connected, it is stretched. Okay, and then when temperature decrease, it comes back to the original length. Okay, this is our basic thing. Next question. A composite block is made of slabs A, B, C, D, E of different thermal conductivities given in terms of constant K and sizes given in terms of length L as shown in the figure. All slabs are of same width. Heat Q flows from left to right through the blocks, then in steady state. Okay, basic figure is given to us. So we are given that we have 4 blocks A, B, C and D as well as E, 5 blocks, and their thermal conductivity are mentioned as well as their length are given. Okay, so we have to find out at steady state what will be the condition. So this question we are going to solve using the thermal resistance concept. Okay, we are going to convert this entire block into a series parallel combination of our thermal resistances. So for that we should be knowing the value of the thermal resistance. So that is based on directly the formula. We can say our thermal resistance that is our R, it is given as our L K upon A. So and they are having same width, so let us assume the width is given as W. Width is W. So we have our 5 blocks. So let us start with our thermal resistance of A will be equal to A is from 0 to 1 L, so its length is L, and K, its constant is given as 2K, and the area will be equal to, it starts from our 0 to 4L, so this comes as 4L times W, and here this L and L cancels out, so we get this as 1 upon 8 kW. Similarly, we can write for our B, and our B starts from our 1L and adds that our 5L. So we get this as our 4L, and its constant is given as 3K, and area will be our, they are basically all are rectangular pieces, so it will be length multiplied by width. Width is our constant, and this comes as our L multiplied by W. And here also this length and length cancels out, so this comes as our 4 upon K times W, and this is our 3. Now we can say our C block, R of C, will be equal to our 4L, and it will be same as B except our width, so that will be 5K multiplied by, that will be our 2L. One second, C is start from 1L to 3L, so this will be our 2L multiplied by W. So here L and L cancels out, so this comes as our, and this is 4, not 5. So here 4 and 4 also cancel out, so this comes as 1 upon 2KW. R of B R of B we found out A, B, C, and we come to D. R of D will be same, and its width is our L, and it is 5K, and this comes into L times W, which will be equal to L and L cancel, so 1 upon 5K W. And finally for our D, R of D will be equal to our L, and this is our 6K times our LW, and giving us 1 upon 6K W. And we can find out the ratio so that we are able to get some values, because this KW, KW and KW are constant with each other. So we can say our RA, RB, RC as well as RD will be equal to, this comes as 1 upon 8 kW, 4 upon 3 kW, 1 upon 2 kW, and this comes as our 1 upon 5 kW, and last is 1 upon 6 kW. So this kW, kW, kW cancels out, so this comes as 1 upon 8, 4 upon 3, 8, 4 upon 3, 1 upon 2, 1 upon 5, and 1 upon 6. And so we can just write in the ratio form. This will be coming as, we can just, this will be, I think, multiply by 120. No, not 120, but this will be our 6, 5, 3. Okay, this will be 40, and this will be 3, 120. So we can write this will be our 15 is to 160, and this will be our 60 and 96. One second, I think I missed something. This is RA 1 by 8, 4 by 3, 1 by 2, RE 1 by 6. What is my RD? Oh, RD is 4L, yes. This is 4L. So this will be becoming 4, and here will be becoming 4. 4 by 5, and one second, let me check again. 1 by 8, 4 by 3, 1 by 2, 4 by 5, 1 by 6. And this comes as our 30, and 60 to 40. Yes, 240, then it's okay. And this will be our 1 by 8, 4 by 3, 1 by 2, 60, 96, and this will be over 12. So in terms of a common ratio, we can write that our RA is equal to 15R, RB is equal to 160R, RC is equal to 60R, and RD is equal to 96R, and RE will be equal to 12R. One second, let me doubt about 1/6. Let me check whether it is correct or not. This is RE, and RE will be our 4L should be here, 24. Yes, that's why it was not coming correct. So this will be our 4L, and this comes as 24W. So this will be our 1/8, 4/3, R/2, 4/5, and this now it's correct. Otherwise, it ratio was not coming. This was our 24. Let me check again. It's a correct one, I think. This is our 24 into 5 into 2 into 3 into 8. $720 and 24 into 12. I think this looks good now. Or I think we can do it otherwise also, because Let me do it again. It doesn't. So we can write that we can just draw the equivalent diagram. So we have this as RA, and from here it will be into three parts: RP, RC, RD, and here will be our RE. And so if H heat is flowing into H heat will be flowing from the out also. And this is HB, and this is our HC, and this is our HD. So from here we can at least say that our H of A will be equal to H of E, and let us suppose that is given as H. So at least option A is correct. Option A is correct. Next is asked the heat flow through the slab A E is maximum. Okay. So let's find out the respective ratio of the heats. So we know that in parallel current distribution, in this case we can write the heat distribution. Heat distribution is inverse ratio of resistances. Therefore we can write our HB ratio, HC ratio, HD will be equal to 1 upon RP ratio 1 upon RC and 1 upon RD. And we get this as 1 upon RP is our let me calculate the ratio actually, otherwise it won't help much. It will take time, but not a big issue. We can find out our 8 into 3 into 2 into 5 into 24. This comes as our 5760 divided by 8. This comes as 4 times 5760 divided by 3, and this is our 5760 divided by 2. 4 by 5 into 4, 757. 60 and we have 1 upon 24, 5760. Okay, so let us divide one by them. So we are divided by 8. This will be coming as 72. So let me write it here. 720, and this is divided by 3 multiplied by 4. Five 760 4 divided by 3 7680, and then it is 5760 divided by 2. And we have 5760 multiplied by 4 divided by 5, 4608. And finally we have our 5760 divided by 24, 240. Okay, then we have to factor out the common one, and we can just factor out our 240 divided by we can factor out 20. Let's check. 408 divided by 20. Nope, there is some problem in the calculation. Let me do it in a different way. I think there is some problem in the calculation. I'm not able to figure it out. Okay, let's do it again. And let's use the basic formula actually. I think there is some problem in the calculation. So we can say that our rate of heat flow is our dq by dt. This is our KLW, and our temperature divided by our length. Okay, here let me write L is the thickness, not the length. L is our thickness and X is our length. Okay. K is constant, W is our width. So first of all, let's find out for our A. So we can say dqa upon dt will be equal to 2 times k multiplied by 4L W, and thickness is our length is our X, which is our L, and the temperature is suppose T1 minus T2, and this gives us 8 kW T1 minus T2. This is for our in this case. Let me define that temperature at the interfaces. Temperature at the slab interfaces are T1, T2, T3 and T4. So we are having 4 interfaces. So we are having temperature T1, T2. So this is our T1, T2, T3 as well as our T4. Yeah. Okay. And similarly, we can write for our interface AB will be equal to, this will be our 3K times LW, and temperature is T2 minus T3, and our 4L, which gives us 3 by 4 kW and T2 minus T3. C will be equal to our 4K 2LW, and this is our T2 minus T3 and divided by our 4L. So this comes as our 2kW T2 minus T3. And now we come to our D, which is our 5K LW, and this is also our T2 minus T3 and divided by 4L, which comes as 5 by 4 kW T2 minus T3. And finally our TQE upon dt, this is equal to over 6K 4LW and T3 minus T4 divided by L, which comes as 24 kW T3 minus T4. Okay, I think yeah. And so at steady state, the heat flow into the system is equal to heat out of the system. So you can say at steady state, heat into the system is equal to heat out of the system. So dQA upon dt is equal to dQE upon dt. Okay. And let me number these equations: 1, 2, 3 and 4, and finally 5. So we substitute this dqa and dqe from equation 1 and 5. So you can say from equation 1 and 5, 1 and 5, we get this as our T1 minus T2 is equal to here kW, and this is our we are having this 8 kW T1 minus T2, 8 kW T1 minus T2 is equal to 24 kW, and T3 minus T4, kW, and this 24 goes by 3. So we get from here T1 minus T2 is equal to 3 times T3 minus T4. Let this be equation number 6. And similarly, we can say that total heat that will be entering the system, let me draw it here only. So we are giving, this is slab A, and the heat from the slab A is divided into 3 parts. This is A divided into B, this is a C, and this is a D. Okay, and finally here we are having our E. So heat into the system A will be divided into B, C, and D. Therefore, we can write that our rate of change of heat of A will be equal to for our B plus for our C plus for our D. And we simply substitute their equations, and this was 8 kW T1 minus T2, and B is our 3 by 4 T2 minus T3, plus C is our 2 kW T2 minus T3, and finally is our D, and D gives us 5 kW, 5 by 4 kW T2 minus T3, and this kW cancels out, so we are left with only 8 T1 minus T2 is equal to 3 by 4 T2 minus T3 plus twice T2 minus T3 plus 5 by 4 T2 minus T3. T2 minus T3 we can take as common, so this will be left with us as 3 by 4 plus 2 plus 5 by 4 T2 minus T3. 4 we can take LCM, so this comes as our 3 plus 8 plus 5 T2 minus T3, and this will be coming as 8 plus 5, 16, 16 by 4. Okay, so we can write this as our 8 T1 minus T2 is equal to 16 by 4 T2 minus T3, and this goes by 4, 4 goes by 2. So we are left with only now 2 T1 minus T2 is equal to T2 minus T3. Let us call this as equation number 7. So we have equation number 6 is our T1 minus T2 equal to, okay, we can substitute T1 minus T2 in this part. So we can say using equations 6, we can put our T1 minus T2 is equal to 3 times T3 minus T4. So this comes as our 6 times T3 minus T4 is equal to T2 minus T3. One second, let me write it here. So equation number 6 is our T1 minus T2 is equal to 3 times T3 minus T4. And therefore we can write that 2 is equal to T2 minus T3 divided by T3 minus T4, which get 2 minus T3 minus T4 is equal to T2 minus T3. So what are the options? So we can say that heat flow, the temperature difference across E is smallest. Heat flow through slab E is maximum. This cannot be correct one. The temperature difference across slab E is smallest. Okay, so smallest difference is our T3 minus T4. So temperature difference is our T3 minus T4 is equal to 1 by 2 . T2 minus T3. I think this is 1 second. T2 minus T3, T2 minus T3, this looks good. 2 times this is okay, this is okay, and this is okay. So this is the temperature difference between, and we can also write that our T3 minus T4 will be equal to 1 by 3 T1 minus T2. So therefore we can say that our difference in temperature between for block C is the lowest one. It is in 1 by 2 as well as 1 by 3. So option C is our correct one. And it says that heat flow through C is equal to heat flow through B plus heat flow through D. Okay. So this we can just easily prove it. And heat flow through C is equal to heat flow from B plus heat flow for D. Okay, we can just use equation number 2, 3 and 4. Using equation 2, 3, 4. And we can say that our dq of C upon dt is equal to, we can just prove it, and it is given as dq by dt plus dqd by dt, and we substitute it. QB is our this will equal to over 3 by 4 kW T2 minus T3 plus dqd is 5 by 4 T2 minus T3, and we get this as our 3 by 4 plus 5 by 4 times T2 minus T3, which comes as our 2 T2 minus T3, and which is nothing but our dqc upon dt. So this is also true. So option D is also correct. So A, C, D are correct. Option A, C and D are correct. I made a mess of it, I'm sorry for that, because the resistance, I think I missed up some important value. I was not able to find it, but anyways, this way we can also solve it. Next question. It was asked in the year 1999, and it states that a bimetallic strip is formed out of two identical strips, one of copper and other of brass. The coefficient of linear expansion of the two metals are alpha C and alpha B. On heating, the temperature of the strip goes up by delta T. The strip bends to form an arc of radius of curvature R. Then the R is. So in this case we have two strips and they are joined together. So let us suppose this is our first strip and this is our second strip, and when they are heated they are going to form an arc. So this is the first one and this is the second one. Okay. And so we can find out the radius of curvature, which is given to us as r. Okay. And because they are having different coefficient of linear expansion, so therefore it is going to bend. Okay. And so let's find out the individual expansion for our copper as well as for our brass when they are not joined together. So we can say expansion for our copper, let us suppose that is our delta L C, which will be equal to coefficient, their origin length and change in temperature. And similarly we can say for our brass, that is where delta LB will be equal to their coefficient, length and temperature difference. Okay. Therefore we can find out that the difference in their expansion in length, you can say that difference in their expansion, let us suppose that is our delta L. Therefore we can write that our delta L will be equal to delta L C minus delta L B. We get from here alpha C minus alpha B and L times delta T. Now when they are bound together, when bounded together, okay, and when they are bounded together, obviously they are going to form an arc, and it is given that the radius of curvature is r. So we are given that radius of curvature is our r, and the distance between the two metal strips is, let us suppose, d. Distance between the two metals is supposed d. Okay. Therefore we can find out that the difference in their arc length, we can say difference in arc length of the two surfaces which is our delta L will be approximately equal to d divided by r multiplied by L. Okay. Because it is a simple formula that our arc difference length is equal to curvature, separation and their base length. Now we can equate this delta L with the difference in delta L, because they are supposed to be same. So we can say equating both differences, we can write that our alpha c minus alpha b delta t is equal to d upon r times L, and we can say that our r is equal to d upon alpha c minus alpha b times delta t. In this case we have assumed that alpha c is greater than alpha b, so for the sake of this we can just put a modulus here. Therefore we can say that it is inversely proportional to delta of t and inversely proportional to our alpha b minus alpha c. So options B and D are correct. Option B and D are correct. So this completes all the 7 questions. I'm sorry for that, I messed up the question. I think there was some problem in the calculation. Okay, I'm not able to find it out, but otherwise we can just use the basic method also, which gives us the dq by dt. Okay, answer we are going to get the same. So this completes all the questions. Thank you.